Up to this point, as we've been dealing with the idea of heredity, we've done so in a very generic way. Yes, we've talked about human traits from time to time, but we've also used many other animals and plants as examples as we've gone through the different types of traits. Our slant now is to shift and talk specifically about ourselves, about human genetics. Humans are a little bit tougher to study than other organisms, and it's not because we're more complicated than other organisms. It's because of some ethical and moral situations. For instance, if you want to know what happens when you made a brown-furred guinea pig with a black-furred guinea pig, you just take those two guinea pigs and you put them together and you wait for nature to take its course. You can't do that with humans. You can't just pick out human one and human two and say, hey, I'd like to see what would happen if you had a child together. So instead of studying the future, as in studying what would happen if two individuals made it together, one of the ways around this in studying human genetics is to instead study the past. By the past, I mean a family chart or a pedigree chart, as is the proper term and is what you're looking at here. There are some basic rules in constructing a pedigree chart, and they're pretty much laid out for you in this example. You can see that males are represented by squares, females are represented by circles, and then you have lines connecting either husband and wife, or at the very least, two people who have had children together. And when children come about, you can see a line drops down, and then that splits and goes down to the two children that are used in the example here. Kind of a unique situation down here in the bottom left, that would be identical twins. The other thing that is important to note, because this is studying the pattern of inheritance, the flow of genes from one generation to the next, is that when an individual is colored in, that means they possess whatever it is, whatever the trait is that happens to be studied. So colored in, an individual shows or expresses the trait, has that phenotype, and if they're not colored in, they lack that phenotype. Here are some additional examples. You can see the multi-generational view of somebody's family going back in the past. Here's a slightly different version of things, because you can see that in some cases there are individuals who are half colored in. That shows a carrier or shows a heterozygous situation. Now, a lot of times this is not done because it just can't be. But in this particular case, they tried to show you an example, and notice they're all female, of carriers. That's the case because this happens to be a sex-linked trait. Therefore, males could not be carriers in a recessive sex-linked trait, as is the case here. But you can see the circles that are half colored in simply represent somebody who is heterozygous. If we go on a little further, there are some videos that you're welcome to watch there. No big deal. This shows you a historical perspective of a royal family and the craziness that went on there. I know you can't see the pedigree real well, but there's some pretty odd family circumstances there. But most importantly, I think we should go backwards. And really the idea here of these pedigree charts is, as I mentioned earlier, to be able to determine patterns of inheritance. In other words, you've learned about a whole bunch of different types of traits: complete dominance, incomplete dominance, codominance, multiple alleles, sex linkage, etc. All of those would show slightly different patterns, and this is the way that some of those patterns were determined, or some of the information about those traits was determined. For instance, if we analyze this particular pedigree, what type of trait is it? Now, I do want to limit the possibilities here. I don't want you to have all those options available to you. Let's just say that we're going to limit our possibilities to autosomal dominant or autosomal recessive. Now, autosomal just means not sex-linked. So just regular old complete dominance, autosomal dominant or autosomal recessive. Now, most of you would look at this, and if those were your only two options, you'd say, oh, the people that are colored in must be recessive because there's so few of them. And although you are correct in this case, I don't know that the logic of recessive meaning fewer and dominant meaning more prevalent necessarily is always going to work. Instead, let's look right here. Let's look at these 4 individuals. Is it possible for these 2 parents to be recessive and therefore these 2 children to be dominant? Well, no, that would be impossible. For this father to be recessive, he would have to be homozygous recessive. In other words, 2 little a's. For this mother to be recessive, the same thing, 2 little a's. So if he's got homozygous recessive genes and she's got homozygous recessive genes, is it possible for them to have dominant children? Well, no, it is absolutely not possible. How did these kids end up with a dominant gene? They couldn't. Neither parent had any dominant genes. But is the reverse true? Could 2 dominant parents have recessive children? Well, the answer to that is yes. If this dominant father is dominant because he has a heterozygous genotype, such as big A, little a, and same thing for the mother, big A, little a, it's possible that each parent donated the recessive allele and that this daughter and this son both ended up homozygous recessive. So the colored in trait must be recessive and not dominant. So that's some of the logic that you're going to be using as we learn about pedigree charts and how to analyze them.